Hello, in this video we're going to talk about conjugate acid-base pairs. We've already talked about this before, but here we take it to the next level and relate strength of an acid with its conjugate base and vice versa. So, a little bit of review, never a bad thing. A conjugate acid-base pair, what is it? So it's the acid and the base that's formed after it donates the H+, or it's a base and then the acid it forms after it accepts the H+ ion. So for example, we have acetic acid in red here on the left and water on the right. And so the acetic acid will donate this proton to water, and water will accept this proton. So the acetic acid is a proton donor, that's a definition of an acid. The water is a proton acceptor, that's the definition of a base in the Bronsted-Lowry definition. Same is true on the right side, the H3O+, the hydronium. It can donate this hydrogen back to the acetate. And so in this case, it's functioning as an acid, and it's donating that proton to the CH3COO-, which is functioning as a base. So if we're going to label this out, acetic acid on the left is the acid, its conjugate base is here, the acetate anion we call it. So it's a pair, a conjugate acid-base pair. And then water is a base, its conjugate acid is the hydronium ion, and they're a pair. All right, let's do another example. So say you have ammonia in water, then what happens? Well, ammonia is a base because it can accept a proton, and so it's going to do that, right? So the ammonia is going to accept a proton, and it's going to turn into its conjugate acid, NH4+. And so that's one acid-base pair. And then the water will function as an acid. It will deliver the proton, donate the proton, and then what's left is hydroxide, which is its conjugate base. So this works here too. Okay, so that's old news. So then let's move on with the new stuff. So the conjugate of a weak acid is actually a base, right? So here's our generic form, right? HA reacts with water to form H3O+ and A-. This is the definition of a weak acid and really the definition of a Ka equation. And so, all right, the HA is an acid. It's going to donate this proton to the water. And then, well, the A- is a base. It can accept a proton from the hydronium. And so you have an acid, then it turns into a base, but then the base can do base things, and it can get kind of confusing. So this is what we're here to work out. So you can also write A- as a base in its own equation. And so this equation is the definition of Kb. You take a base and water, and it protonates the base. In this case, it turns it into a neutral species from a negative species, but you still added a proton, right? The proton is donated from this water to this A-, so the water's the acid, and then the A- is the base, and then you get the conjugate acid over here on the right. Now, do notice that these two equations are not just the reverse of each other, which means the Ka equation and the Kb equation are not just reversed from each other, because water is present as a reactant in both of these equations. And then on the right side, one of these is producing H3O+, hey, that's an acid. One of these is producing OH-, hey, that's a base. All right, so these equations are not just the reverse of each other, but you can take a weak acid, turn it into a conjugate base, and vice versa. All right, so then now what's the relationship between these two? Well, let's try this. Let's try multiplying them together. I kind of know what the answer is, so that's why I know to multiply them together. So then we take the forms of both of these and throw them next to each other with a multiplication sign, okay. Now the A-'s cancel, and so do the HA's. And so we're left with the product of Ka times Kb is equal to the product of hydronium times hydroxide, which, hey, that's Kw. That's the autoionization constant of water. Like, we know this number already. And so we can make this a thing, right? Ka times Kb is equal to Kw, for sure. Now, mind you, this is not an acid and some other base, right? This is an acid and its conjugate base. You can also do this in terms of P, right? So pKa plus pKb equals 14. Basically, you just take the negative log of both sides and plug the number for Kw in there. So you can do that too. So Ka and Kb for a conjugate pair, remember, acid and its conjugate base, or base and its conjugate acid, you take the Ka and Kb together, They're inversely related. Since they are multiplied equal the same number, or they have to add to the same number, if you make one bigger, the other one has to be smaller. So stronger acids, which means a bigger Ka, have weaker conjugate bases, a smaller Kb. And stronger bases, which would be a larger Kb, have weaker conjugate acids, a smaller Ka. And so this kind of symmetry, in a way, is best visualized in this chart, I think. So let's start up here. So you got HCl. That is a strong acid. So that strong acid, its conjugate base over here is chloride ion. And the chloride anion is pretty much ineffective as a base, right? HCl is so strong that its conjugate base is just, it doesn't do anything. You put chloride in water, it doesn't change the pH at all. It's not a base. Now, kind of in the middle, this is the territory of the weak acids over here. And so weak acids, their conjugate bases are still pretty weak. They're weaker than the acids themselves, but it's not negligible anymore. If you put fluoride anion into water, like say sodium fluoride or something like that, it will make it basic. It is a base. And we get into that in a subsequent video, right, about the hydrolysis of salts and how that affects pH. Right? This comes out to be very important, right? This would be basic in solution. The flip side's true. Here's the domain of the weak bases. That box sucked. There's weak bases. Their conjugate acids are even weaker, but they still function as acids. So if you take ammonium, which is a cation that you can get, right? You can get ammonium chloride, things like that, right? You take ammonium, put that in water, it's going to function like an acid with the Ka and all that stuff, right? Not a very strong one, but it will still do it. And again, that has big implications. And then down here, right, if you have sodium hydroxide or something that's a strong base, its conjugate acid is just useless and does not affect the pH of water at all. So again, this idea is really important. We don't get to it until a subsequent video. Here's a nice table that shows a whole bunch of values, right? The stronger weak acids are on the top, and the stronger weak bases are on the bottom. And there's this kind of continuum again, like we just saw on the last chart. How Ka and Kb, and thus pKa and pKb are related to each other, right? The products of this times this equals 1 times 10 to the negative 14th. The sum of that plus that equals 14 within experimental error. Okay, a couple example problems and then we're done. So which one of these has the strongest conjugate base? Well, what does that mean? So strongest conjugate base means weakest acid, because they're inversely related in that way. And then the weakest acid, well, that has the lowest Ka. So then we just need to look down this list and find the one of these with the lowest Ka. Let's see here, -5, -4, -5, -4. Hey, here it is. All right, so this one has the lowest Ka, and thus it's the weakest acid, which means it'll have the strongest conjugate base. So that's how you would do that kind of problem. And now here's this one. Identify the conjugate acid of HPO4 2- in this reaction. So this one's a little messier, and so we kind of have to dig into this to figure out what's going on. And so, so we're talking about this hydrogen phosphate, this thing. Well, let's see here, PO4. Where do we see PO4 over here? Hey, there it is. Okay, so we found PO4. So now that means these are going to be related somehow. Let me clean this up a little bit. So these are an conjugate acid-base pair. So which one's which? Let's see here. This molecule over here only has 1 hydrogen. This has 2. So in this process, it means that this hydrogen phosphate over here on the left accepted a proton to become H2PO4. And so that means if this is the one that accepts the proton, that's a base. And then this is its conjugate acid. All right, so then that means, if this is a base, that means this is probably an acid. And then that makes sense because this hydrogen right here is going to come off, right? It's an acidic hydrogen. Nitrous acid is a weak acid. And then its conjugate pair is over here. So this is the conjugate base of this weak acid, because the acid donates a proton, and then you're left with the conjugate base. Okay, so we've sorted out what's happening here. The proton goes from here, boop, onto there. Great. Now, what is the question again? Let's see here. The conjugate acid of this thing. Well, it's a base, so great, this makes sense. So its conjugate acid is that, H2PO4-. And so that's sitting down here, C, H2PO4- is the conjugate acid of HPO4-2-. Okay, so that's what we have for this video. And then further, what happens next is the fact that the conjugate acid of a weak base is legitimately an acid. That will affect the pH of solution, so then we learn how to do calculations of, okay, you put some salt in water that contains the conjugate of something, and then how does that affect the pH? Because that becomes important at times. And so we get to that next, but for now, that's all I got. Thanks for watching.